So let me pay the TA.
Not TA, but
Not the TA, but
Thank you.
volunteer TA. The real TA, Jiu Chin, is at a wedding. Okay, so today's lecture is going to be a little bit technical. Okay? I'll try to emphasize the principles over the technical details. Let me though start by redoing the tail end of Tuesday's lecture, because that stuff was quite important. In fact, historically, what happened was at SLAC in, I guess it must have been the 70s. I'm not quite sure. It might have been the late 60s. They saw that some of the electrons hitting, say, stationary proton targets bounced back more than they should have. And that was basically a repeat of the Rutherford experiment, where Rutherford sent alpha particles into gold foil, and he found more of them bounced back. That meant that they experienced strong forces. The only way they could experience strong forces is if they were scattering off objects that were point-like, because only a point-like thing gives you a small r, so that a 1 over r squared force gets to be huge. So what happened at SLAC was the electrons were bouncing off something that was point-like, and that was, they realized at some point, and I don't think it was by any means immediate, that they had discovered the particles that Gell-Mann and Zweig had hypothesized, namely quarks. But that stuff, I think it was still a little bit uncertain until they then did, well, I can't give you the history exactly, but another experiment they did at SLAC was the one that I was describing at the end of Tuesday's lecture, namely to measure E plus E minus goes to Q bar, and take the ratio of that to E plus E minus goes to mu bar. And what they found was a result that was basically 3 times bigger than they thought. And that indicated that there was a color factor of 3, which is, well, I'm leaving out something though, because when Gell-Mann and Zweig originally put forward the quarks, they were thinking in terms of quarks that would fit a, well, they were thinking actually quarks such that you put 3 of them together and make a nucleon and so forth. And somebody, I forget who it was, pointed out that you really only have 3 quarks in an S state if they were fermions, if there was an extra quantum number, and such that you could have 3 different ones in the S state, so you would have something totally anti-symmetric. All right, anyway, that's all been, I guess I've gone on a little too long about that. And so let me repeat some of this then. Sigma E plus E minus goes to mu plus mu minus. This thing, at least at tree level, is 4 pi over 3 E center of mass squared, alpha squared, where this is the fine structure constant, and this we call sigma 0. And then for the ratio of the 2, you would have sigma E plus E minus goes to Q bar divided by sigma E plus E minus goes to mu plus mu minus. Well, the difference would be, first of all, a factor of 3 for color, and then you'd have to consider what the charges were. So for an up quark, you have charge 2/3, down quark charge 1/3, and of course the thing would be squared. And here I'm just thinking of E plus E minus photon Q bar. And then at slack, they were I think I suppose when they did the experiment at first, they might have been below the energy needed to make the charm quark, which was discovered jointly at Slack and at Brookhaven in more or less the mid-70s. In any event, if we include the charm quark, then we get another one, and then we have the strained quark. And in the text, Schwartz is talking about experiments not done at Slack, but rather done at LEP 1, where they had the E plus E minus collider, and that machine was designed originally to test whether the Z and the W existed. And so it had to have a center of mass energy of at least 90 GeV. And in fact, they were able to then increase the energy up to, I think, something like, he says 205, right? Yeah, GeV. In any event, that's enough to have another bottom, to have the bottom quark, but not enough to have the top quark. And so altogether, this is 3.67. Now, at these energies, you also have to include the Z. And this makes a bigger contribution because, in particular, instead of having 2/3 and 1/3, you basically have larger quantum numbers like 1. And the result is that the total ratio goes from 3.67 at tree level to 20.09. And the actual experiment, again at LEP energies, let us say between 90 and 200 GeV, was 20.79, or 3.5% higher. This 3.5% can be associated with gluons in the final state, and I'll get to that in a moment. Notice one thing, however. What did they measure in the final state of Slack? Did they measure quark? No. In fact, that's one of the real puzzles of modern physics is why the quarks are confined so tightly. Well, this one is a too long. Anyway, the idea here is that for processes of small action, the QCD can be treated perturbatively, and consequently we have a computation, a tree-level computation that more or less works. In fact, it's good to within 3%. And in fact, I haven't even put in the gluons, right? In fact, I've neglected the gluons completely here, and still it's good to 3%. What happens is, as these guys go out and and you consider this process at large time and space, in other words, large action, the Q turns into pi mesons and k mesons and whatever, or possibly even, I guess, possibly even baryons. And so that the, now, how does this happen? Well, one way of thinking about it is the up and down quarks are pretty light compared to the scale of energies we're talking about. And the strong force is quite strong, at least on large distance and time scales. And so you can pop QQ bars into existence so that instead of having Q and Q bar, you have QQ bar here and QQ bar there, those are mesons. So you have pi mesons, basically. And they come out then as not just one, but a whole bunch of them. And these are called then jets. The idea that you can factorize this thing into a perturbative vertex and then a process of hadronization. This is called factorization, that you can, the small action part is perturbative, the large action part is mysterious. Okay. Now, what are these final state corrections to get the extra 3% to go from 0.09 to 0.79? And the idea is you have gamma or Z going across, and then in the final state you can have an extra gluon. And so wavy line, gamma, Z, loops, like our Secretary of the Treasury's signature, is a gluon. And so you have that diagram plus that diagram and plus, so loops going from one final state particle. And what happens is that if you compute these, you see that there's an infrared divergence, but when you compute the cross-section for QQ bar goes to gamma Z plus soft gluons, and you add all three together, the infrared divergences cancel. In fact, the first two, so the first two final states, this one plus that one, gives something like sigma R, which is R0 sigma 0. And R0 is basically the 3 times this big bracket. And then the gluon factor is 4 alpha S. That's basically G squared over 4 pi, where G is the strong interaction one, divided by pi, a C sub F, which actually is just a half. I don't know why Schwartz persists in putting in Casimirs instead of ordinary fractions, but he does anyway. Mu tilde, this is a subtraction point. And this is the 4 minus D. We're doing dimensional renormalization. So 4 minus D is about a 10th. And this is then 1 over epsilon squared plus 13 over 12 epsilon minus 5 pi squared over 24 plus 259 over 144 plus order epsilon. And let me just remind you, epsilon is the same thing as 4 minus D. So we need to keep track of that. On the other hand, this one gives you sigma V, which is the same thing, minus 1 over epsilon squared, minus 13 over 12 epsilon, plus 5 pi squared over 24, minus 29 over 18 plus 4 epsilon. Okay, so almost everything cancels, but not everything. And one gets a finite correction. And what's called sigma next leading order, in other words, one thing beyond beyond tree level. Well, it's still tree level, isn't it? No, one loop. Okay. Anyway, it's sigma 0 plus sigma R plus sigma V. And this sigma 0 has got to be this whole thing here, not that sigma 0. So I'll just call it sigma. this turns out to be the R0 sigma 0 and then 1 plus 3 over 4 pi alpha s, and then C sub f, which turns out to be 4/3. And so this thing is R0 sigma 0, 1 plus alpha over pi, alpha strong. Okay, well, the advantage of doing this calculation is that then we see that what alpha strong over pi is. It's whatever you need to go from 0.09 to 0.79. And it turns out that that alpha strong is 0.11. And in fact, it's 1184 if we go to better measurements. And this, of course, is a running coupling constant, and so we're talking about this at mz. At the z mass, it's 0.12 actually. And at that same z mass, alpha electromagnetic is about 1 over 129. And the running coupling constant itself, there's a nice picture in the book, although I think you can get a much better picture if you just Google running strong interaction running coupling constant and add PDG for particle data group, and that will flip you to a suitable place. 0.5, 0.1, this is alpha S. This is Q, this is a log scale, 1, 10, 100 GeV, and it basically does that. And the thing has been, if you look at the figure, you see a lot of dots and squares and circles and so forth, indicating that in fact this thing isn't just something somebody dreamed up, but actually it was measured. Measured in the sense of measuring the cross sections experimentally and then comparing all these perturbative calculations and figuring out what alpha S has to be at different values of Q, different center of mass energies. And in fact, it was down here where the original Slack experiments were done, and then we got to the higher values. Okay, the next topic then is precisely this running coupling constant. Let me warn you, by the way, that there's a typo in the first printing of the book, where the quark masses are listed. They're said to be in GeV. In fact, the quark masses there are actually in MeV. And in the 2014 printing, that was corrected. I sort of have two versions. I have an electronic version that's convenient because I can print it just carrying one chapter around rather than the whole damn book. All right, so now we're going to talk about this running coupling constant, and in order to do that, there are two things that are involved. The first is that basically one has to analyze the renormalization of all of, actually all of the, well, the way Schwartz does it, he analyzes all of the 2- and 3-point functions, figures out to lowest order, order G squared, say, what all the counter terms have to be, and then says, well, this stuff can't depend upon the subtraction point, and as a result, we get a value for the running coupling constant. I don't know. I think that's actually the hard way to do it, but since that's the way it's done, I'll just describe it. But I think there are simpler ways of doing this. Anyway, let's look at the first one is this. The first one is so we're thinking of the gluon propagator, and this is called MF. F because it's a fermion loop. The next two-point function is one that does this. It's a gluon loop, and what do we have here? We have a 3-gluon vertex here and there. And so this is called M3. And then there's this one, which is easier to draw, but it's not quite obvious what it is, but this is a 4-gluon loop, 4-gluon vertex. And so this is called M4. And then there's the Halloween diagram. There's a ghost loop, and this is called a ghost. And then finally, there's the counter term, which is meant to fix all the 1 over epsilon terms in all of these diagrams. In other words, the mid-dimensional regularization of 1 over epsilon poles. And so that one is wacko, and this is called M-counter. And the actual two-point function is has color and space-time indices, and it's the sum of all 5 terms. And mercifully, Schwartz sets C to the 1, so you're in Feynman gauge, and the gluon propagator then, mu nu, and I guess I should put AB here, is delta AB minus I beta mu nu over p squared plus I epsilon. So that's the photon propagator. Okay, now let's look at some of these terms. I am fermion. This is the fermion loop, the fermion loop inside the gluon propagator. And this is then, turns out to be minus equals minus trace TA, TB. These are the TA, of course, is lambda A over 2, and lambda are the 3 by 3 Gell-Mann matrices that occur somewhere in IG squared for coupling constant at each vertex, and then an integral d4th k 2 pi to the 4th I over p minus k squared minus m squared I over k squared minus m squared. That's the easy part. Then there's a trace, gamma mu, k slash minus p slash plus m, gamma mu, k slash plus m. Okay. So that's the picture. Now it turns out that if you look at this, you see, well, that's pretty much like QED, because in QED we had a photon, a fermion loop, and a photon. So that was basically analyzed, and one can extract from that the value of this thing. And so you get that MAB mu nu for this fermion loop is delta AB, or 1/2. And this 1/2 is something that Schwartz calls TF, and it's the normalization. It's the thing for, if you said trace TATB equal delta AB big TF, and that's actually delta AB over 2. So TF is just a half. And then we have G squared over 16 pi squared. So in other words, what Schwartz does is he extracts from the previous treatment of QED, extracts what this has to be. And what we have then is P squared A to mu nu minus P mu P nu. And then notice if you contract this with a P, you get 0. And here you get minus 8 over 3, 1 over epsilon, minus 20 over 9, minus 4/3 log mu tilde squared over minus P squared. And mu tilde is related to mu, the subtraction. The next one is I am 3AB mu nu, and this is the one looks like this. And this one is simpler actually. It's G squared over 2 and integral d4 k over 2 pi to the 4th minus I over k squared minus I over k minus p squared, and then some structure constants A, C, E, F, B, D, F, delta C, F, delta E, D, and then N mu nu. And the N mu nu is, I'm not going to write it all down, I'll just give you the flavor of it. M nu is G mu alpha P plus K rho, and two other terms that are similar. All right, I've switched from eta to G because Schwartz persists on using G. So if I stay with G, G alpha beta, G rho sigma, and then G nu beta, P plus K sigma, minus dot dot dot. All right, so it's a complicated thing involving, it's quadratic in momentum and some high quartic in flat space matrices. Just to introduce some, not to introduce, but to remind you of some of the notation. If you have the T's in the adjoint representation, now in the adjoint representation, instead of being 3 by 3, they're 8 by 8 matrices. And this is then C adjoint Casimir, the 1, but this 1 is an 8 by 8 matrix. Anyway, CA is actually equal to N, which is 3 for SUN, for SU3. Okay. Well, I don't think I'll write down exactly what that loop was. Now, I am for AB mu nu. This turns out to be just 0. And it's 0 because it's basically proportional to an integral d4 k over, well, we're saying proportional, we have to get the 2 pi's right. So this is k squared. Now, the point is, in dimensional regularization, we just set this equal to 0. What's going on is that, in a sense, a pole here cancels a pole there, and effectively it's 0. All right. Anyway, going on from there, we've got the ghost loop. The ghost loop is actually somewhat simpler. It's I am ghost AB mu nu, and so you have gluon, ghost, gluon, and this turns think without the I, it turns out to be a -1 from the, because you have a fermion loop. A minus g squared, and then an integral d4k, 2 pi to the 4, and this is I over k minus p squared, I over k squared. So this is p coming in, and if that's k, this is p minus k or k minus p. Anyway, and then some structure constants, f cad, k mu, f dbc, and then k minus p nu. So that one has potentially quadratic divergences. Anyway, if we add all these things together, what we have is MAB mu nu equals, and it's delta AB g squared over 16 pi squared, AB mu nu g squared minus p mu. And what Schwartz focuses on is the part that we don't want, namely the 1 over epsilon terms and the mu-dependent terms. But he wants these because he wants to know, he wants to be able to figure out what the counterterms are in order to cancel these divergences. And so what you get here is CA, which is another complicated way of writing 3. 10 over 3 epsilon plus 5 over 3 log mu tilde squared over minus p squared minus the number of fermions times Tf, which again is 1/2, and then 8 over 3 epsilon plus 4/3 log of mu tilde squared over minus p squared. So in other words, the thing is all of that plus a finite piece. And I'm actually moving along here pretty rapidly. I think I should slow down. Okay, so now I'm going to... Any questions? No questions? Ah, good. Let me get the fresh candy. I bought some Friday night. Good catch.
So we have this MAB mu nu, and our AB are color indices, and mu nu are spatial indices, right?
Let me see, I didn't get that.
So on MAB mu nu that we're dealing with right now, we have our
this
AB,
thing here is the sum of all of these diagrams.
and our AB are color indices.
AB are color, and
mu nu are spatial.
Mu nu are space-time, and the AB are color in the adjoint, so they go from 1 to 8. Because
And
we're talking about A coming
Yeah.
in and B going out.
does up and down mean anything for A and B?
Up and down? No.
Yeah, that's what I thought.
For compact groups, you can ignore up and down.
Yeah.
Structure constant, totally antisymmetric, real, and you can forget up and down.
Yeah.
It's, if you have a non-compact group, then what you have is TA, TB is I, F, ABC, TC.
Yeah.
And then that C is relevant. Okay. But you still have anti-symmetry in AB, even if it's non-compact. Okay, let's look at the Lagrangian now, or the action density, in which we have all of the renormalization terms. So I'll write it out. -1/4. Z 3 du a nu a. So this is the renormalized field. That means that it has the nice property. And this is just a quadratic. Then we have Z2. And now we have Z sub m times the physical mass of the core. And then psi I. And then we have minus Z3 C. And we have ghost, box, ghost. So that line is the quadratic part of the action density. Now we have the cubic part, minus G Z A3, or A cubed, I guess is the way you write it, that's better notation. FABC, D mu A nu, AB AC mu nu. Minus a quarter G squared Z H A to the 4 F EAB AA mu AB nu F ECD AC mu AD nu. And because this is done in such a way that Schwartz persists on leaving all the space-time indices down and raises the color indices, where in fact we should leave the color indices down and raise and lower these indices. So what you really want is, this thing is a scalar, so for every mu down there's a mu up, and for every mu down there's a mu up. I'm copying Schwartz, so I'm a little bit wrong here. And then the last term here is, well, the last two terms are plus G Z1 AA mu psi bar I gamma mu TAIJ psi j plus G Z 1C, C for ghost, FABC D mu C bar A B mu C C. And that has a nice form to it. You see, you have FABC and you have ABC. All right, now, let me just mention something about these Z's. Zi is 1 plus delta I. That's just a notation, but Schwartz shifts from Z's to deltas at some point, and if you don't remember this, then you can't follow. All right, so he's doing MS bar dimensional regularization to get the Z's straight, find out what all the deltas are, find out what the Z's are, or the deltas. And he does these calculations in a way such that he's really only concerned with getting the epsilon, the 1 over epsilon terms, and the mu tilde terms so as to be able to figure out what the counterterms actually are. And one thing that he uses is the dimensional regularization notion that if you do the integration of 1 over k to the 4th in d dimensions, you get I over 8 pi squared, 1 over epsilon plus something finite. All right, now the vacuum polarization graphs are those things with the gluon two-point function, and there are 5 different processes. And what he finally gets is MAB mu nu is delta AB, A to mu nu, p squared minus p mu p nu. And then p squared over 16 pi squared CA 10 over 3 epsilon minus NF TF 8 over 3 epsilon minus delta 3 plus something finite. I'm just going to write F as finite. Okay. So what is delta 3? Delta 3 is exactly the inverse of, additive inverse of that. In other words, delta 3, which is the same thing as Z3 minus 1, is whatever cancels this term, which is 1 over epsilon g squared over 16 pi squared times 10 over 3 CA minus 8 over 3 NF TF. In other words, exact, so that this whole thing is finite. Okay, so that's what Z3 is. So all that was the gluon to gluon two-point function. If he now considers the quark two-point function, and of course you can have a gluon go like that, and in computing this he uses the relation sum over A, B, K, and L of TA, and these TAs are the L1s, lambdas divided by 2, TB, JL, delta AB, delta KL. This turns out to be a sum over A, TA, TA, IJ, and that's C sub F delta IJ. And C sub F in general for SUN is n squared minus 1 over 2n, which is 4/3. All right, now, so this was just something that goes into this calculation. What he finds basically is that I, sigma 2, ij of p slash is delta ij c sub f ig squared an integral d4 of k over 2 pi to the 4 gamma mu k slash plus n k squared minus n squared plus I epsilon gamma mu minus I over k minus t squared minus n. Oh no, there's no n squared. That's because that one is the blue one plus I epsilon. And what this turns out to be, again, dimensional regularization and so forth, is delta ij. And if you just keep the infinite part and the mu-dependent part, what you get is g squared over 4 pi, 16 pi squared, c sub f, 2p slash minus 8m over epsilon plus delta 2 p slash minus delta m plus delta 2 times m plus something finite. All right, so from that, he extracts that C2 minus 1, which is delta 2, is well, all right, let me just write that. 1 over epsilon g squared over 16 pi squared minus 2 c sub hat. And basically, he's saying that this term has to cancel that term. This term has to cancel this term. And so the other one is delta sub m then turns out to be 1 over epsilon g squared over 16 pi squared minus 6 c squared. But there's also, he also analyzes the ghost gluon propagator now, and he finds that delta 3c, the ghost counter term, is 1 over epsilon p squared over 16 pi squared c squared. So at this point, he's got several of the counter terms, but not all of them. Let me just get a drink of water, and meanwhile, does anybody have a question? By the way, when I wrote down the action density there with all the z's, everything was finite except the z's. All right, the next thing.
Yeah. So he's just looking for additive constants to cancel out the divergence.
Right, he's trying to identify what the counter terms are.
Right. What's the ZM then? I'm missing now.
Well, it's just a counter.
Oh, I
see
see
every.
Well, I didn't see it in the Lagrangian. I see it now.
Okay.
I'm sorry.
It's that every term in the action density has a counter term.
Okay.
Okay. Now, what about 3-point functions? Well, one 3-point function is gluon in, quark, anti-quark, and now that would just be finite. So in order to have a problem, we introduce a gluon going across. And then there are two other diagrams. One does this. But we don't see any quarks in the final state, so what we do is this. And then the next one is simply where there's a counter term. Okay, well, this one gives us the following. Z1 minus 1, which is delta 1, is 1 over epsilon g squared over 16 pi squared minus 2c sub f minus 2c sub f. So that identifies delta 1. So now, what we're going to do is we're going to look at the fermion-gluon part of the action density, and what we get then is a mu to the 4 minus d over 2 g Z1 A mu A psi bar I then mu PAI J psi J. And let me just go back here a second. Okay, it's this term here. What's been done here is the mu was introduced in order to be in d dimensions. So in 4 dimensions, the mu term goes away. But if we are looking at this from the point of view of dimensional regularization, then we put in this mu to get the dimensions straight. And now we're going to rewrite this as mu to the 4 minus d over 2. And remember, 4 minus d is epsilon, which is the order of a tenth. G Z1 over Z2 square root of Z3 I'm a little puzzled about is we had a Z1, we're making a transition from fields to bare fields, and so we should factor out a constant for each one of these. And all right, I guess what happens is the Z, you get a square root of Z2, I guess, from each of these guys. All right, so it looks like this. A0, 0 meaning bad. Psi bar 0 I, gamma mu, J, psi 0 J. All right, so these fields are what we call bare fields. And so if we were rewriting this in terms of bare quantities, we have G0, AA0 mu, psi bar 0, gamma mu, TA, psi 0. And so we identify G0 with this. So what we've got is G0 then is GZ1 over Z2 square root of Z3 mu. I'm just going to write it as epsilon over 2. This 4 minus d is kind of silly because we're going to use epsilon anyway. Okay. Now the point is that G0, the way some people think of this is the action density, pure action density, divine action density, I don't know what to call it. But anyway, it's before we mucked up with dimensional regularization and introduced a mu. So G0 is mu independent. So one way of going at the renormalization group is to say that G0 doesn't depend upon mu. And so that's mu d mu. And what's G0? Well, G0 is GZ1 over Z2 square root of Z3 mu to the epsilon over 2. And remember that Z sub I is 1 plus delta sub I. And, okay, so what is this? Let me just say what this is. When mu, dd mu acts on the last term, well, dd mu of this is just epsilon over 2 mu to the, all right, let me do it explicitly. It's mu to the epsilon over 2 minus 1 times epsilon over 2. right? Mu d d mu on this. Okay, it's that times z1 over z2 square root of z3 and times g. And then we have plus mu d d mu time, and in fact that's mu to the, let me try to get this really straight here now. So I have mu d d mu on this times that, and that's it. And so this just restores epsilon to the mu d epsilon over 2. And then what we have here is mu to the epsilon over 2, I'm pulling that out, times mu d d mu of gz1 over z2 square root of z3. All that's 0. And now what is beta of g? Well, beta of g is mu d d mu, one way of writing it, g. And so there's a g right here. So this thing is plus mu to the epsilon over 2, and then mu d d mu of g, well that's beta of g, but then that's multiplied by z1 over z2 square root of z3, right? By the way, I'm departing a bit from my notes, so check. All right, wait a minute. Now I've really gone off the rails. All right, let me follow my notes. What we get then is the beta of g, which is mu d d mu of g, has to be minus g mu d d mu of z1 over z2 square root of z3 mu to the epsilon over 2. All right, let's just follow my notes. And so then this is minus g mu d d mu of what? Well, it's 1 plus delta 1 over 1 plus delta 2 square root of 1 plus delta 3 mu to the epsilon over 2. So I'm redoing some of this, but it was too complicated for me to do it on the fly. Okay, now these deltas, of course, are all infinite, but we're going to imagine they're actually small. And so what we have here then is, and of course, the derivative of 1 is 0. And so this is minus g. Now the d d mu on the mu epsilon over 2 is going to give us epsilon over 2. And the rest of that is going to be mu d d mu of 1 plus delta 1 minus delta 2 minus delta 3 over 2. So all of that is beta function. And actually, I think what we've done here is we've said, after we've done the differentiation, we've said, well, mu to the epsilon over 2, epsilon is 0, so this is just 1. That's why it went away over here. And there. So it's sort of gone everywhere. Okay, so in other words, what we get is beta of G is G times minus epsilon over 2 minus mu dt mu of delta 1 minus delta 2 minus delta 3 over 2. Okay. Now, we want to translate from d by d mu to d by dg. And these deltas, how do they depend upon mu? Well, the deltas, let's go over here. The deltas, are a g squared and then a 1 over epsilon. And I'm trying to find the mu dependence.
If you change from mu to dg,
What's that?
don't you have to have how g is dependent on mu?
Yeah.
And that depends on G.
Say where?
Well, the delta depends on G, and G depends on.
Right,
does
delta
G-
depends on G.
And how does g depend on mu?
Yeah, that's what I'm trying to find.
Okay.
Well, you wrote.
How G depends on mu.
You wrote G.
Oh, here.
Where?
G0 here. G0 is mu independent, right? You said G0 is mu independent. So
Yeah,
we
all
have-
right, okay. So if we imagine all these guys are 1, that's right. Like that's what I've got written on the back here, yeah. So in other words, suppose we say that G goes as mu to the minus epsilon over 2. Then we can say dg du is minus epsilon over 2 mu to the minus epsilon over 2 minus 1, right? And we can say that dd mu, I think I did the wrong one. It's ddg times dg du. Ah, there's dg du. And so dg d mu is minus epsilon over 2. And now I'm going to set the epsilon basically, and the epsilon equal to 0. So this is 1 over mu dg.
Yeah, G.
All right?
The first part is 1 over mu times G, right? Because dg d mu is actually minus epsilon over 2 1 over mu times G, right? Because
It's, yeah, there is a mu to the minus epsilon over 2, but I'm ignoring that, because epsilon is 0, nearly. I think I can get away with that. So, in other words, mu dt mu is then equal to, I mean, maybe I've got a mistake, minus epsilon over 2 ddg. All right. And all of these, so in other words, what we've got is that beta of G is G times minus epsilon over 2. So minus epsilon over 2 plus epsilon over 2 ddg
Delta 1.
of all these things, and we can leave out that. So that's just delta 1 minus delta 2 minus delta 3 over 2. Okay. On the other hand, Schwartz has an extra G there.
Yeah, that's weird.
What?
It's from the differential because actually G is proportional to mu to the minus epsilon over 2.
So you're saying I shouldn't have thrown that away? Oh, that'll give us another G.
Yeah.
Yes! Brilliant. Okay. So this gives us
G over mu.
Yeah.
another factor of G. And so now we get another G there. Okay, great. So I owe you guys some candies. Hold on. You get 2. Whoops. And somebody else got one. Who asked a question? Did you get one?
I made a comment.
Oh, you did several?
Just one. That's one is okay.
What about you? Do I owe you one? No?
Well, you asked the color and space.
Well, I already got that one.
Oh, you already got that one. Okay.
All right.
Try to load.
Okay, so now what we finally have here is we're really running out of board space. We basically have this. Beta of G is minus epsilon over 2 G plus epsilon over 2 G squared BDG of delta 1 minus delta 2 minus delta 3 over 2. But all these deltas depend upon 16 G squared over 16 pi squared. And so what we actually have here is minus epsilon over 2G plus epsilon over 2G squared EdG of 1 over epsilon G squared over 16 pi squared. And now something that we minus 2CF minus 2CA plus 2CF minus 10 over 3CA. Well, we're running into another expression here. Plus 8NF over 3 TF. Well, let's see. I'm going to have to erase something somewhere. Let's erase those. All right, I'll write it down here. What we get then is beta of G altogether is minus epsilon over 2G minus G cubed over 16 pi squared. 11 over 3 C sub A minus 4 over 3 N sub F T sub F. All right. So what does this tell us? This is, of course, how the beta how G is varying as mu, which might be mz or some other point energy, how it's varying, and you see it's going down. It's going down unless you have a lot of flavors, and the number of flavors that you need in order to get it to go positive is 17. And okay, so we've basically run out of time. This is the running coupling constant. This is actually the equation, and we can then put in, we can then integrate this equation, if we set beta 0 equal to -11 Well, I don't know. Do you want to see me integrate the equation, or should we just quit for now? Maybe we'll quit for now, and then in the beginning of next time, I'll integrate the equation and we'll tidy this up a little bit. It's worth doing it a second time. Okay, so we can turn it on.